Suppose I have two sets and I wish to see which set has more things in it. One way I can do this is to count, but notice how I don't have to do this and simply match the elements up one to one. We know that the set of primes are only a part of the set of whole numbers, and this must mean there are more whole numbers than primes. But one of the beautiful things about infinite sets is that this is not the case. They are the same size. We can match them up one to one forever. These are what we call countably infinite sets because we can put them on a list and count them. The same thing can be done for the even numbers, the odd numbers, and even the fractions. But now assume I've made a list of all the real numbers from 0 to 1, and some man comes and tells me that my list is incomplete. How? He takes the first digit of my first number and changes it, the second digit of my second number and changes it, the nth digit of my nth number and changes it, all the way to infinity. His number disagrees with every single one of my numbers and at least one digit. He has proved to me that the set of numbers from 0 to 1 is unlistable, it is uncountable, it represents a larger infinity than anything we've seen before. But now I would like to introduce you to a new set called the Cantor set. Take the numbers from 0 to 1 and remove the middle third. Now call this line left and this line right. Now remove the middle third again from these two lines and call this line left left, left right, right left, and right right. Now from these four lines, keep on removing the middle third all the way to infinity. The Cantor set is simply the set of numbers in 0 to 1 that are never removed if we do this till infinity. But now it's not hard to see that any random, arbitrary, infinite string of L's and R's must correspond to at least some element of the Cantor set. All we have to do is follow the instructions till infinity. Here are some examples, and let's make a list of all these combinations. Now the same man from before comes and yet again shows us our list is incomplete by creating a new combination. He takes the first letter of our first combination and flips it, the second letter of our second combination and flips it, the nth letter of our nth combination and flips it, all the way to infinity. His new combination disagrees with all of our infinite combinations on at least one letter. He has proved to us that the Cantor set is infinite. Now here's the really mind-blowing part. What is the length of the Cantor set? Well, it's simply what we started with, 1, and we subtracted 1 over 3 from it, and we kept subtracting the middle thirds, getting this following infinite series. Now this series will eventually converge to a number that is smaller than any positive real number, so the Cantor set must converge to 0. The length of the Cantor set is 0. Now take a moment to digest what I have just said to you. It is absolutely stunning, mind-blowing, and paradoxical. Infinity truly works in mysterious ways. We had a set of length 1. We kept taking away from it until its length was 0, and we still ended up with as many numbers in that set as we started with. We can literally fit as many things on something that has 0 length versus something that has an infinite amount of length. But if that is the case, then why does length even matter? What does length truly mean? How does the 3-meter line differ from a 4-meter line if we can fit the same amount of things in them? But that is a story for another time. Until then, it's time for you to go exploring. Thank you.